in MOSFET. What do we mean by this? Channel length is made small. Okay, and what is going to be the consequence of making the channel length small? Why do we want to make channel length small? It's because as the technology improves, we always want to build smaller sized transistors, and therefore we will be able to pack more number of transistors within a given area in the silicon wafer or chip. So the entire wafer is divided into different blocks which are called dies, and in each die you make one chip. So if the transistor size is made small, then we can pack more number of transistors within the given area in the die, and thereby increase the functionalities which are possible per unit area. So that is always the case with miniaturization. Right now you must be knowing that we are reaching like 3 nanometer technology. That means one transistor, by 3 nanometer we mean the length of the transistor, which is L, channel length, that is between 2n plus region in this case. So that is the MOSFET length. Of course, for 3 nanometer the transistor is not the same. It is a different kind of transistor that is being made, but still just for your understanding sake, by length we mean channel length, from drain to source, the distance the electrons travel. So that is what we mean by channel length. So when we reduce this channel length, there are various consequences. That is what we are going to look at. So number one, which we have already seen, is channel length modulation, that we saw in the last class. Channel length modulation. But for completeness sake, let me rewrite the expression for ID-SAT. Channel length modulation is more prevalent for larger values of VDS, and we have the drain current expression ID is equal to mu n Cox. This is in saturation what I am writing, divided by 2, then W by L, what was it, VGS minus VTH, okay, whole square. And this was the original expression for the drain current that we derived, and then we corrected it in order to include what is called as channel length modulation, and that term is basically 1 plus lambda VDS. Okay, so which means that the saturation current also depends upon VDS. It's not completely independent of VDS. If it was completely independent of VDS, lambda will be 0. Once it saturates, there will be no more variation of the drain current. But practically what we see is that there will be small dependence, and this dependence will be more pronounced when we reduce the channel length, because we know that lambda is basically, or lambda into VDS is basically delta L, okay, delta L by L. Okay, it's a fractional change. So if L is smaller, then delta L by L is going to become more prominent. Okay, if L is very big, a small delta L change will not give rise to larger change. Okay, so it depends upon L, what is the value of, so for say 22 nanometer MOSFET, the L is 22 nanometer, and then which means that a delta L change, say by 5 nanometer, then 5 by 22 will be more significant compared to a 1 micrometer MOSFET, which you can think of as a long channel. So 5 nanometer divided by 1 micrometer, it's like 5 by 1000, and that fraction is very negligible, and therefore lambda is very close to 0 for large values of L. So we can neglect this term, the contribution or the change introduced by this term for large length devices, but it is more prominent for small length devices. So lambda depends upon the length of the device, okay, as you can see here. So this expression is basically giving you the saturation current, and we have seen this and we have derived the expression also, right? So second short channel effect now we will go into, which is called velocity saturation. Okay, velocity saturation. Here by velocity I mean the drift velocity. Okay, drift velocity. Now in the derivation of MOSFET current we have used the concept of drift velocity. It was basically dx by dt, rate of change of position of the electron with respect to the time, and that depended on what? So drift velocity d is given us, so vd, so that's a drift velocity, is given as the expression is mu n. For electron usually it is in the opposite direction, so minus mu n into E. So what does that mean? The mu is a constant, so the drift velocity is going to increase in proportion to the electric field that you apply. So this is always the case. Whenever a current flows through the conductor, there will be a flow of charge carriers, and the speed with which these carriers move is, this is basically an average speed. Drift velocity is basically giving you an average speed. If there is no collision, what is going to happen is that this charge will get accelerated in the field, and the velocity is no longer going to be constant. It will keep on increasing, like F is equal to ma. If you apply Newton's law, then we know that point particle with charge in an electric field is going to accelerate as long as the force is there. But this is not the case when the carriers move inside, electrons or holes, when they move inside the semiconductor material, there are going to be various other phenomena like scattering. Scattering means it will collide with the vibrating ions of say silicon atom, and silicon atoms will be like vibrating in its position because of the temperature of the material. So due to that vibration, there will be an interaction of these electrons which are moving through the crystal, interacting with this vibrating core of the atoms, which will basically minimize or it will basically oppose the acceleration, and that will result in an average speed which we call as the drift velocity. So this drift velocity is proportional to electric field, okay, usually. But as the electric field increases and increases, there, if I draw a graph which is basically plotting the electric field magnitude versus the drift velocity. So as per this equation, it has to be a constant like this. As we increase the electric field, the drift velocity should also increases. But in practice, what happens is that this linearity will not continue beyond a certain value of electric field. So there is a particular value of electric field, that's, we can call it as some kind of critical field, beyond which it will not increase as expected. So there will be a saturation, and this velocity corresponding to, so the value or the magnitude of the drift velocity saturates at some point. Okay, so beyond EC, if you increase the magnitude of electric field, the drift velocity will not increase. So this I will call as VD sat. That means it's a small v, which is velocity, drift velocity, saturation value. So this relation is not valid. So this is valid only for E less than EC. Okay, but for beyond EC, this is going to be VD sat. Okay, and E is greater than or equal to EC, it is going to be saturated. That means it is going to remain constant. So this is what we mean by the phenomena of velocity saturation. Now what is the consequence of this in the case of a MOSFET? MOSFET current is due to the flow of electrons. If we are considering N MOSFET, the flow of electrons result in the drain current, and we have derived the expression which was basically, so if your VDS is less than say VGS minus VTH, that means it's working before saturation, then our IDS was what? It was mu n C ox W by L VDS into VGS minus VTH minus VDS by 2. So this was our expression. You can take VDS inside and then it will be VGS minus VTH into VDS minus VDS square by 2. Okay, so that is another way of writing it. But whatever it be, this was the expression that we derived before the current expression, before the saturation is reached. And if you want to include the effect of channel length modulation, you can also multiply it with this factor, though it is not very significant for smaller values of VDS, but still you can put in this. Okay, the effect contributed by the last bracket may be very negligible for smaller values of VDS. Okay, this may be closer to 1. Okay, so this was our expression for linear region or quadratic region. This expression is valid. Now if you put in the picture of velocity saturation here, now I can relate the electric field. We know the electric field E is what? It is basically VDS by L, right? So electric field is going to be VDS by L. So corresponding to the critical electric field, okay, so corresponding to the critical, I am ignoring, I am only taking the magnitude. So the magnitude of the critical electric field will be related with some value of VDS, and that we will call as VD sat, okay, VD sat. So VD sat divided by L. So what is VD sat? In other words, we can say that VD sat is the value of VDS at which the drift velocity is saturated. Okay, so as the electric field increases, the drift velocity will be saturated, but now we are writing the electric field in terms of voltage VDS applied. Electric field is going to depend upon VDS by L. Now we are looking at short channel effect, so L is going to be smaller, okay, and that means your electric field is going to become larger for a given VDS. As you reduce the channel length, then the electric field is going to become bigger and bigger. So if L become in nanometer, so earlier if it was in micrometer, you may have smaller electric field when you apply 1 volt. 1 divided by 1 micrometer. So your electric field is what? It will be 1 divided by 1 micrometer, which is going to be 10 raised to 6 volts per meter. Okay, but if you reduce it to say 100 nanometer, from 1 micrometer, if the length is reduced to 100 nanometer, it will become 10 raised to 7 volt per meter. And suppose this electric field is say, I'm just taking as an example, if it is equal to 10 raised to 7 volts per meter, if EC is that, then for a 100 nanometer length MOSFET, when you apply 1 volt, you will reach the saturation, beyond which the speed will not increase. So what is the consequence of the current? The current will be saturated. Okay, so therefore the ID SAT, okay, so ID SAT due to the velocity saturation, so this is the drain current due to velocity saturation, is going to be mu n C ox W by L VD SAT. Okay, I am replacing VDS with VD SAT. What is VDS? The value of VDS at which drift velocity is going to be saturated. So if you apply even larger VDS, there is going to be no change in the current, because the speed of the electron is no longer going to increase. So it will be same whenever it is going to be VDS is going to be larger than VD SAT. Okay, so it is going to be VGS minus VTH minus VD SAT again by 2 into, but in this expression it will be still lambda VDS. Okay, so because this is actually coming from delta L by L, which is equal to lambda VDS. Okay, so that is not related to VD SAT. Okay, the extension of the depletion region width, which we learned in the last class, that depends upon the actual value of VDS. It is not going to depend upon the VD SAT. Okay, whereas in the other part, this is actually the current which we derived, where we assumed that the potential of the electric field is going to be given by VDS by L. Okay, so that is how this VDS came, but this VDS comes from delta L by L. So the source of these VDS and the other VDS are going to be different, and therefore here in this place we will continue to put VDS. Okay, whereas wherever the electric field is related or mean the current is going to depend upon the electric field, which we substituted as VDS by VD, like wherever we have used this relationship, so that is in the derivation of this part, we have used VDS by L as E, electric field. Okay, so there the velocity saturation will limit the rise of the current, and therefore we put VD SAT there. So it is the earlier equation, only difference is that at 2 points I have put or replaced VDS with VD SAT. Okay, so this is still the equation for VGS, or let me write it as when VDS is smaller than VGS minus VTH. That means there is a saturation of the current even in the supposed to be quadratic region. The velocity is going to be saturated. So let's draw it and see how does it look like. So I am drawing VDS here, and this is my ID. Okay, so let's take two different cases. One case you have a very small VGS value, and if you have a small VGS value, it will saturate like this. Okay, so this what is going to be this is going to be the point at which it is going to saturate. Before that it is this, and we can write it as basically VGS minus VTH. Okay, so VGS1. Okay, so this curve corresponding to some VGS, which I call it as VGS1, which is a smaller VGS. So it saturates, and suppose my VD sat is here. So this is my VD sat, where my velocity is going to get saturated. Okay, it will correspond to some voltage, and I'm going to say that it is here. So for this VGS1, the saturation has already happened even before VDS is reached. So VD sat is not playing any role here, because the device is saturated, because VGS1 minus VTH is the point at which saturation happens, and VDS, when it crossed there, already saturation happened. But now let me take a higher value of VGS, so that let's say VGS2, so that VGS2 minus VTH is larger than VD sat. So that will be the case that will be more interesting. So it is going like this, and then it is supposed to go like this, and then saturate like this. Okay, so the saturation is supposed to happen here. And what is this point? This is the point where VGS2 minus VTH. Okay, so I am writing here VGS2 is greater than VGS1. Okay, much greater than VGS1. So this much is the difference, as you can see here. So the saturation should happen from here onwards, but then there is a VD sat. Before we apply VDS to become equal to VGS2 minus VTH, there is a point at which VDS become equal to VD sat, and once you reach there, the velocity saturate, and therefore the current already saturate here. Okay, so this is going to be the way in which saturation is going to happen. Okay, so it cannot decrease, it will be saturated. Okay, so let me draw it more properly. Okay, so instead of saturating at this point, it has saturated early, because your VD sat was here. So at this point, when you applied VD sat, your electric field reached the critical electric field, and therefore your drift velocity is saturated. And once the drift velocity is saturated, you cannot have any further increase in the current with respect to VDS. Okay, so that is why we are using this expression. Okay, so now we have a new expression for current, if you take into account of the velocity saturation phenomena. Now we had earlier two expressions, one corresponding to the saturation current, the other corresponding to the current, drain current before saturation. Now in addition to that, we have another current. So we need to combine all of this into one equation for for easiness in writing. So we have what is called as a unified current model. Okay, unified current model, which means that your ID current is going to be written as one equation. Okay, and it is valid for all the values of VDS. Okay, so we don't need to write separate equation for velocity saturation, the normal saturation when VDS become greater than VGS minus VTH, and then VGS minus VTH is smaller than VD sat. So there are basically three ranges, right? One is so if you look at there is a range. If I consider the top curve, then there is a range between this, then there is a range here, and there is a range here. Okay, so depending upon whether your VD sat is whether it is after VGS minus VTH or before that, you have to pick up the right equation. So instead of writing different equations for different conditions, let's try to combine all this into one equation, and that is basically given as mu n C. mu n C ox and then W by L. Okay, I'm going to write in a slightly different way. I'll write K n so that I can introduce that also. K n dash. Okay, so K n dash W by L and then V min. Okay, I'll explain. V min into VGS minus VTH into V min minus V min by 2. Okay, so this multiplying 1 plus lambda VDS. Okay, so this is my unified current equation, where I need to now define what is V min. What is V min? It is the minimum of three things. One is VGS minus VTH. If I substitute V min as VGS minus VTH, we get the saturation expression. Okay, that is this bracket will be or this V min into this first bracket will become like VGS minus VTH the whole square, or it could be VDS, or it could be VD sat. Okay, minimum of these three. Okay, so we have three different so, and of course I have a case of current equal to 0 also, when so that is not combined in this equation. So if I want to say that 0 when VGS is less than VTH, so still I have two cases, but if VGS is greater than threshold voltage, we have only one equation, not three equations. Okay, so depending upon the case, so for example for this curve and this curve, if you look at for this curve, the current is determined, I mean, as you increase VDS, earlier we have the linear region where you just put VDS there, and once you cross VGS minus VTH, then you have VGS minus VTH for this region. So we don't put VD sat for the bottom one. Okay, whereas on the top curve, we never put VGS minus VTH, but we will use VDS and VD sat. Okay, so that these are the ways in which, so depending upon the value of your so here we have a different equation, similarly here we have a separate equation. So different curves here will have different it will have different expressions. Okay, so for the bottom curve, for VGS1, we need to consider VDS, this one and this one. This is for bottom curve, but for the top curve, we need to consider VDS, this and this. Okay, so these are for VGS2, and this one is for VGS1. Okay, whatever I have ticked. So whatever is relevant will be taken according to the minimum of these three. Okay, so that will be put in the expression as V min, and now I also need to explain what is Kn dash, so which I did not introduce earlier. So Kn dash, as you can see by comparing with the earlier equation, it is basically mu n C ox. And what is C ox? C ox is basically epsilon ox, that means the permittivity of oxide, divided by T ox, and we consider it as one parameter, and this is also one of the SPICE directive. Okay, I asked you to put say Kn and Kp for correspondingly for P MOSFET, so you can put in the values, and this is generally a process parameter. Okay, or you can say the technology parameter or the process parameter. So in VLSI, there are there is a division of work into two group. Certain parameters are fixed by design engineers, and certain parameters are fixed by the process engineers. Now, who are design engineers and who are process engineers? Process engineers are the people involved in fabricating the device. So there will be a fabrication lab. Examples are TSMC, Taiwan Semiconductor Corporation. Then maybe Samsung will have its lab where chips are manufactured, or maybe Intel will have another one. Okay, so there are different global players which will fabricate the chips, and they will fabricate the chip if you give the design to them. Okay, a properly designed circuit, if you give to them, they will take your design and they will fabricate it for you. And when they fabricate your device, there are certain parameters which are fixed by them, and you can't say anything about it. It is up to their technology how that parameter is going to be decided. So for example, the oxide permittivity, it depends upon the material which the people are going to use when they fabricate. Okay, so the fab lab will use certain material, and that will decide your epsilon ox. And similarly, how much is the thickness of your oxide layer, you have no say on that. Okay, if you are a design engineer, you have no say on that. It will be decided by your fabrication lab. Okay, so the fabrication lab or the technology lab, where people are involved in making these devices, there are certain parameters under their control. So Kn is one such parameter which is under their control, which whatever they say, you have to put that in your model and use it. Okay, so in SPICE directive, you have an option to specify what is your Kn. I have shown you that, and you have to see what is the dependence on the on that parameter, how the current is going to change depending upon that. So basically, if Kn is increasing, your current is going to increase. So Kn can be increased either by increasing your epsilon ox, or by decreasing your T ox. So how they are going to do that, that is up to them. Now the design parameters, for example here W and L, that is something which you can decide. Okay, you can specify you want to create a transistor with this much W and this much L. Okay, so you can specify that to the technology people, that this is the kind of transistor I want, though you don't have any say in telling to them what is going to be the oxide thickness. You cannot say that, but you can definitely tell them, I want a transistor, I want you to make a transistor with this much width and this much length. So that is something that, but still the technology people will say, this is the minimum I can go. Okay, I can reach up to a length which is as small as say 20 nanometer. I cannot make a transistor smaller than that. Okay, but given that limit, you can decide whether it should be 50 or it should be 100 or whatever. So the minimum length is decided by the technology people, but you have a control over deciding above the minimum length how much it has to be. Okay, and this is very important in the design of digital circuit. How do we decide about the W and L values? So they are called design parameters. So W and L are called design parameters, and Kn in this case is a process parameter. Okay, and both of this you can specify. So in that LT space, if you have done the experiment, you will see that some of the parameter you can specify by right clicking on the device. So those are basically your design parameters. Okay, W and L, all of this you can specify there, but through SPICE directive, if you want to if you want to put in or change the parameter, so those are technology parameters. parameters or process parameters. Okay, so this is basically our second short channel effect. And what is it? It is called velocity saturation. So saturation can happen in two different ways. One way is that your VDS become greater than VGS minus VTH. That means pinch off happens. Okay, saturation due to pinch off and saturation due to velocity saturation. So velocity saturation is because your electric field has become very large such that it has reached the critical field where your mobility where your drift velocity can no longer increase further. Alright, so next we will go to the third short channel effect, and the third short channel effect is called drain induced barrier lowering, and the people in the field in VLSI will refer to it as DIBBLE. Okay, it's just the short form of drain induced barrier lowering. So when you hear DIBBLE, you just know that they are talking about drain induced barrier lowering. Okay, what is it? Okay, so to understand this, we need to draw some schematics here. So if you go back into the schematics, so you have there's an N plus region here, and this is also one of the short channel effects. So I will draw in such a manner that you will see that your channel length is very small, and there will be a depletion region extending into this like on both sides. So this will be the depletion region, and this is one is source and the other is drain, and then you have oxide and metal. Okay, so metal I will draw there shaded. So this is my metal or gate. Okay, so there will be, when there is no voltage applied, there is a depletion region extending into the P substrate. This is an N channel MOSFET, and then as you apply VGS and VDS, we know what happens. VGS will decide whether an inversion layer will be created or not, and VDS, what does it do? It will basically increase the depletion region width. Okay, so as you increase VDS, it's like reverse biasing a junction, and your depletion region is further increased. So this will be the way in which it will look like. Okay, and now if VDS is large and depletion region width is increasing, it will majorly increase into the P substrate region. Okay, it will not increase into the N plus region much, because N plus is like 2 orders of magnitude higher doping there, and therefore wherever the doping concentration is less, that is where you will have your extension of the depletion region. Okay, so this will effectively reduce the length of the channel. Okay, and the reduction is very significant for low length MOSFET, right, or smaller length MOSFET. This reduction is going to become very significant. Earlier it was like this, and it has almost become half. So in order to invert this channel, if you want to apply the gate voltage, you don't need to apply the same amount of threshold voltage as before, because you don't need to invert the entire region from source to drain. You have a smaller region to invert. Okay, so you only need to invert this much region. So if you want to invert a smaller region, then you require only smaller amount of electrons coming up there, and in a way you can say that your threshold voltage will be reduced by it. Okay, so there will be depletion region here also, but the inversion. So let me show the inversion with the red color. So you have only a small region to be inverted in order to create in order to go into the strong inversion. It is more easier now, and you can achieve it with a lesser threshold voltage because effectively your channel length is reduced. So drain voltage reduces the channel length, thereby reducing the VGS required for strong inversion, and that is what we mean by drain induced barrier lowering. Okay, now in order to see this more clearly, we need to also look at the the energy band diagram if we can draw, but now we will draw it from left to right. Okay, how the energy band changes along this direction. So we can draw that, but through the surface we will draw the energy band diagram, how the energy bands are at the surface from left to right. Okay, earlier the way we have drawn energy band diagram, if you remember, it was vertical, that is oxide, then silicon dioxide, metal oxide semiconductor, right? So we drawn like this. That was the way in which we taken the dimension, okay, x earlier, but now I want to take it horizontally and draw this energy band diagram. So let me just do that. So if you go from left to right, you have an N plus region. Okay, so there is an N plus region, then there is a P region, and then there is N plus region. Now first thing to draw is the case where VDS is 0. Okay, so VDS is 0, your Fermi level is going to be continuous. Means when there is no voltage applied, your EF is going to be same. Now N plus means the Fermi level is going to be very close to the so this is our Fermi level, and it is going to be very close in the N plus region. It is going to be very close to the EF, right? Then this is my EC. So EC is going to be very near so this is EC on the N plus region, and whereas the Fermi level is going to be more near to the EV. So this is my EV in the P substrate, and then I will have EI and I will have EC. So just like I draw it for PN junction, it is an NPN. Okay, just like a transistor, the energy band diagram will look like that of a transistor. Okay, so let's draw the intrinsic level here also. So the intrinsic level is going to be, so I'm taking a small channel length so that the P region is relatively smaller, and my, so this is my EI here, and this is my EV here. So same thing here also, EI. Okay, so right now I have not applied any potential across drain and source, so that is why all EV on both sides should align like this. They should be aligned, and here also they should be aligned. Okay, so now I can join it. So this is the depletion region 1, that is source to bulk or source to the semiconductor, N plus to P, and then back from like this. and this is my intrinsic level, how it is changing, and then finally it will look like this. Okay, so roughly it is like this. So this is my EV in the N plus region, this is also EV in the source region, so this is drain region, and this, so this is how it will look like when we do not apply any VDS. Okay, the moment we form this N plus region on the P substrate, it will look like this. Okay, so you can see that this N plus region, it is majority carriers are electrons because your Fermi level is close to conduction band. Okay, and here it is Fermi level is close to valence band, so it is P type. Again, in this side, on the drain side also, because of the N plus region, the Fermi level is close to conduction band. Okay, now on the top of this, now if I apply the potential, I said earlier the depletion region width will increase. So how can you show that? Okay, so in order to do that, let me redraw the energy band diagram. In the case when you apply VDS, okay, what is the consequence of applying VDS? One thing you know, that this Fermi level cannot be continuous. Okay, it will be shifted between the two region by an amount equal to the applied voltage or the corresponding. So if you apply a positive voltage on the drain, we know that we are drawing electron energy band diagram, and as a consequence your EF is going to go down. So this is EF on the drain side, and it will go down corresponding to the EF on the source side. And this difference, okay, this difference is basically Q into the voltage VDS. Okay, so if you positive voltage apply, it will go down on the drain side. Okay, that's because Q is negative for electron. Okay, what about the other? So the regions are still N plus P and N plus. So what is going to happen is that so if you redraw, your EC is still here, your EC is going to be here, and then so this is your EC on the drain side, EV on the drain side, and then somewhere middle you have your EI of the drain side. Similarly you have so this is EV or EC on the source side, and then this is your EV on the source side. Somewhere in the middle you will have your EI on the source side. Now what is more important is to draw how does it look in the middle. So as before, in the source side there will be no much change, it just goes up. It will just go up as before, but then on this side what is going to happen is the depletion region is going to extend. So earlier the depletion region was on the right side, it was this much is the depletion region, and it was more or less same as what was on the right side, on the left side. So but now the situation will be slightly different. There will be much more depletion region on, so the left side it will be same as before, but on the right side, because of the large change, now I have to draw something like this. Okay, so the depletion region has extended so much into it, and every other band will follow this. This is the intrinsic, so that will also follow that change. Similarly, you have so it may not look very nice. Okay, so somewhat like this it will look like. Okay, so as you can see that the depletion region width is very large, the way I have drawn here. Okay, now it is increased like this. So as I told you, initially it was a thin depletion region, which was like this, but now it has increased by very large because of VDS increasing. That has extended, so the transition region corresponds to the depletion region, and it is extended into the P substrate, not much into the N plus region. So that is why I have encroached into this channel region. Now what is drain induced barrier lowering? So earlier the barrier was this much, so this was our barrier. Okay, now because of this encroachment of the depletion region, as you increase the depletion region more and more, what will happen is that at some point of time it will basically pull down this like this. It will reduce the barrier. So we had a barrier which was somewhere here earlier. Okay, it was something like this. It was like this. If I redraw what was earlier, and then it was something like this. Okay, but because of the application of large VDS, what has happened is that the depletion region is extending into the channel region. That is one thing, and then as a result the energy band will be bending downward more and more. Okay, as more and more encroachment happens, what will happen? This barrier height will be reduced. So the barrier height reduction happens. So this is what we refer to as barrier lowering. So now the barrier is only this much. This is the new barrier. So in a way, if you draw the energy band diagram, you can see the effect much more better way. So here I have drawn the energy band diagram in this direction. So this is my x direction. Okay, so all this levels are corresponding to the surface of the semiconductor. I am drawing the surface region from left to right. How does the energy bands vary? So as you increase VDS, the consequence is that the depletion region extent, the bands on the right side goes down by an amount equal to the applied VDS into Q, and as a result in the channel region there will be barrier lowering. So drain voltage induced barrier lowering. So this is what we mean by DIBL. So now the question is this. Okay, so if this is what is happening, then what is going to be my threshold voltage? So that is a question we need to answer. What is the new threshold voltage? Okay, so what was the earlier threshold voltage? That we will denote as VTH0. So VTH, okay, let us write it as VTH. So earlier threshold voltage was what? VTH0 plus, you remember this gamma we talked about in the last class, due to body biasing. Okay, there will be a correction. So VTH 0 is the threshold voltage without body biasing, but if there is a body biasing, then we need to take into account. So if there is a source voltage with respect to the bulk, then we need to add that to your psi s, and then minus your psi s. Okay. So where your psi s is 2πb. Okay, so this is what we have seen earlier. Now this will be further modified, okay, because of DIBL, or drain induced barrier lowering. So how much we need to modify this, we need to look at. So in order to see that, so we will do one thing. So we will so again the consequence of drain induced barrier lowering upon the threshold voltage is actually found out by measurement. Okay, so we apply VDS at two different values. One is a small VDS value. Say, let's say that let VDD, okay, that is the power supply voltage, be the power supply. So in digital circuit we will have a 0 voltage and VDD, which is corresponding to low and high states. Power supply high voltage, high state voltage. Okay, so there will be two levels, either 0 or VDD will be available. So let VDD be a power supply high state voltage, and if we apply VDS equal to, so if VDS is equal to VDD, we apply, and then we measure the VTH. How do we do that? We just do the characteristics, and from the characteristics we can find out what is going to be the VGS, right? As you increase VGS beyond some point, keeping your VDS constant as VDD, at some point of time your current will become significant. Okay, the device will be turned on, and notice that value of threshold voltage. Okay, so if VDS equal to VDD, then you evaluate your VTH. Okay, so your VTH you will get some value. So let us call that value as so if it is a very high so VDD, if you apply, definitely it is going to be in saturation. So we will get a VTH which we will call as this VTH we will call as VTH SAT, because the device will enter into saturation because of the high VDS that we applied. We have applied VDS equal to VDD, that is the highest voltage, and your VGS, as you increase, the device will be turned on at some point. Okay, but the device is definitely going to be in saturation. Okay, because your VGS is going to be or VGS minus VTH. VGS minus VTH is going to be less than VDS in this case, right? So VGS also maximum, it can be VDD only. Okay, so even if you apply VDD also, it will be in saturation, because VDD minus VTH is anyhow less than VDD. So we have fixed VDS as VDD, and then we are finding out the threshold voltage, and the threshold voltage that we get with the saturation condition, we call it as VTH SAT. And similarly we take another voltage VDS equal to, say, some small voltage, say 0.1 VDD. Okay, say very small voltage, or 0.1 or 0.05 VDD. So that is like a very small voltage we are applying, and then we find out the VTH for that voltage, and whatever is the VTH that you get, so this we will call it as like linear. Okay, why this is because this is going to operate in linear, because VTH is going to be or VGS is going to be greater than VDS, because I have applied VDS very very small, so that when it is turned on, you have your VTH definitely VGS minus VTH is going to be greater than VDS. So this is saturation mode. I find the threshold voltage in saturation mode by applying large VDD or large VDS. VDS is equal to VDD, the maximum possible, and also applying small VDS, I find the saturation voltage, and this corresponds to linear mode. Okay. Now, what are we looking at in Dibble? In Dibble, we are looking at basically the variation of the VTH is what we are looking at. So, how much is going to be the variation of the threshold voltage? So these two threshold voltage, we are going to claim that they are not going to be the same. So which is going to be larger and which is going to be smaller? So definitely when you apply large VDS, it should be smaller by the logic which I said, because we can invert we only need to invert a smaller region because of the lowering of the barrier. We only need to invert a smaller region, or in other words, from energy barrier point of view, what you can say is that when you apply the gate voltage, you are basically pushing down this region. All the bands here you are pushing down by applying VGS. So VGS will push everything down, because positive VGS means this region will be pushed down. Now if you want to push it further and further, such that electron can easily flow from one side to the other, so that this region will also become n-type. If you push further, keeping the EF constant, you can push it down by only applying VGS and make it to n-type, and thereby invert the channel. So that is basically the way in which the threshold voltage is defined. How much you need to push it down such that it will become an n-type material in the middle region. So if it has to be made n-type material, how much we need to push? So how much voltage you need to apply in order to achieve that? But if already the barrier is gone down, so we don't need to push that much as before. We only need to push only a little bit. The present new barrier, that much only we need to push it down in order to make it n-type. So our VTH will reduce when we have large value of VDS. So we will define a parameter, the Dibble parameter. Therefore Dibble parameter you will define as, say, eta. So that is going to be equal to V TH linear, this is going to be larger, minus VTH saturation, this is going to be smaller, because we don't need to push down much because the barrier is reduced, divided by the difference in the VDS values. So VDD minus, say in this case we have taken 0.1 VDD. So whatever is the VDD that you take, you can say that very small VDD. Okay, so this is a parameter that we will find out by experiment. Okay, so what is the experiment you need to do? After fabricating the device, you apply VDS is equal to VDD, find the characteristics and find out the threshold voltage. So that is one threshold. Then we apply smaller VDS, and again repeat and measure the threshold voltage again. So they will be different by some amount. If they are same, then Dibble effect is not there. If they are different, definitely there is barrier lowering. That's what we mean by that. So we can find out the eta, which is the Dibble parameter, and once we find out this eta, then what we can do is that we can modify so our threshold expression. So the new expression for threshold is basically our earlier VTH0 into gamma into the source to bulk or body voltage plus psi s minus psi s. So this was our earlier expression. Now we need to subtract eta VDS. Okay, so we have seen how it depends upon VDS. So as VDS is changed, the threshold voltage is changing. We are assuming a linear change, and the rate at which it is changing with respect to VDS we have found out. By taking 2 point we can find out the rate at which it changes, and then how much we are increasing it depending upon that. So if this is VDD, then we will get basically VTH sat here. So this rate multiplied by VDS, so that will tell you the effect of drain induced barrier lowering. Okay, so this is our new expression. So this is also a short channel effect, because for long channel, basically the width or the length of this region, this is our length, right? Length of the channel. So this will be very far away, and thereby some fraction of or this same amount of depletion region encroachment will not make much effect if L is like very large and this is only like say 1/100th of the length. But if it is like 1/10th or 1/5th of the entire length, this is going to be very significant. Now how to overcome this phenomena, because it is not a good thing to have this effect. So we need to basically do something to avoid this effect. So to overcome Dibble effect, we can introduce certain change. Okay, what is the change that we introduce? We can introduce P plus region near the N plus region. Okay, so the idea is basically to reduce the length by which the depletion region is going to extend into the channel region. Okay, so if it is a P plus material, so if you have a PN junction, basically it is a PN junction. So you have N plus region here. Earlier it was P region here. So as you have it, for example, if you think of it as a diode and you are reverse biasing the diode like this, then what happens is that since it is N plus, the depletion region will be very much less extended to N plus region, but it will extend a lot more into the P region, because in the P region the carriers are like very scarcely populated. The density is very less, whereas here you have very, very high density. So everything can be obtained with a smaller length. So you can have WP and WN, that is the width of depletion region into the P region and the N region, and then you can write NA into WP equal to ND, that is the donor impurity concentration, into WN. So if NA, so in this case our NT is much, much greater than NA. That is why it is extending so much into the P region. So to overcome this effect, what we can do is so this is our P side, but near to the, we will introduce a third region, which is basically P plus region. And then if so it is a P plus and N plus region. And if you now reverse bias by the same amount, the picture will be much different. Okay, so there is going to be a depletion region here, but it will be very, very small, and this side also it will be very, very small. Okay, so thereby the depletion region is only extending this much region. It will not extend because we are introducing a P plus region there, whereas here the depletion region has extended so much. Okay, so by introducing a P plus region, we can reduce the depletion region extension into the into the channel region. So the channel length is effectively not much affected by it, and therefore the barrier will also be not reduced. Okay, so the barrier reduction is now reduced. Thus the barrier reduction is reduced as the extension of the depletion region into the channel is now minimized. Okay, so we are proposing this. Okay, introduce a P plus region, so there is a P plus region. Okay, so P is there, P plus is there, and N plus is there. Earlier it was only P and N plus. So this is done on both sides, both source and N side, so in order to keep the device symmetric. I told you in an earlier class that you can use any of the terminal as drain or source, because MOSFET is constructed as a symmetric device. Okay, so that is about the other effect, that is Dibble effect. Now let's go to the next effect. This is again or the fourth short channel effect. This is called sub-threshold leakage. Okay. Now, by the term sub-threshold, you should immediately understand that VGS is less than VTH. Or to be more precise, we should say that VGS is between VTH and 0. So what is going to happen if we keep the VGS less than VTH, okay, but greater than 0? So sub threshold, less, sub means smaller than threshold, or just like we say sub micrometer. Sub micrometer means it is referring to lengths which are smaller than 1 micrometer, like say 100 nanometer, etc. So here sub threshold means VGS is less than VTH. Okay, so what is going to happen if this is the case? We need to look at the picture inside the device. So we know that if you simply draw the transfer characteristics, we did that earlier. So that is VGS versus ID, and by using the SPICE directive, we have been able to fix our threshold voltage. So threshold voltage is somewhere here, okay, say 0.8 or something like that, and say this is in microampere. We are looking at this drain current. So we got an expression something which looked like this. Okay, this is something that you got. Now in our case we kept the device in saturation, and therefore we had basically a curve which looks like a parabola, right? We got something like this. But if suppose your when we did the experiment, what I am saying is that we kept our VDS as VGS. So as you increased VGS, you have increased your VDS also. Okay. Alternatively, so if this is the way we do, we get a parabola, because we ensure that the device is functioning in the saturation region, and therefore your current ID is basically mu n Cox W by L, there will be a 2 here, into VGS minus VTH the whole square. So this is what we will get. I mean, I'm neglecting all the short channel effects, but if VDS was kept as constant, you used a second power supply and you applied a fixed voltage, say for example 3 volts you applied, and then you varied your VGS from 0 to say 5 volt. Okay, so initially the device is going to be in saturation mode, and so it will trace this path like a parabola. Okay, this path is like a parabola, and then after some time what will happen, your VGS is increased such that your VGS minus VTH is going to be larger than your VDS. So for example, if VDS is 3 and VTH is so let's take a say 3 volt, and let your VTH is equal to 0.8 volt. So when your VGS is equal to say 3.8 volt, what is going to happen? Then your VGS, or greater than 3.8 volt, your VGS minus VTH is going to be larger than VDS. This means linear region. And if it is linear region, the current is not going to be a parabola like this. It is going to look like this. It will be like a straight line, it will look. Okay, so this is the way you will get the characteristics. You have not done this, but you can check this. If you keep your VDS as constant, and then at some value of VGS, that is say 3.8 volt. Okay, so this is basically VDS plus VTH. Okay, at that voltage you will have a change in the shape of this characteristics. From being a parabolic relationship, it will turn to a linear relationship. Okay, that's because from saturation it will, where this is the current equation, it will go to the other equation. It may be a smooth transition, okay, from parabolic to this linear. It may be a gradual variation, not an abrupt variation, but still there will be variation. So that you can observe when you do the experiment. Okay, so the point is that if you plot it, the characteristics like on a linear scale. So here I have taken a linear scale. The current is plotted in linear scale, and you have an option to do logarithmic scale also. Now if I draw the same characteristics, not in a linear scale, but on a logarithmic scale, all I am going to do is basically you take a logarithmic sheet and plot the same thing. Okay, so this is again VGS, but now in y-axis what you do is basically log of ID. Okay, this is logarithm to the base of 10, And then what is going to be seen is going to be entirely different. So if I look at this, so these are some of the critical point. Okay, one is VTH and the other is where it goes to linear. So what you will observe is a straight line here, and then it will bend like a saturation like this, and then it will further bend like this. Maybe more gradually. Okay, so this is what we are going to see. So this is our VTH. So only difference, it's the same characteristics, only difference is that I am using a logarithmic plot. Okay, earlier it looked like it was zero current, okay, but now you will see that it is no longer zero current. Okay, so there is and you can even extend this further to left also. Okay, so this region is not having zero current, that is the region between 0 and VTH. So VTH may be 0.8, so 0 to VTH, if you look at there is going to be current like this, okay, in the logarithmic scale. And now in logarithmic scale, probably you are aware that the scale is going to change like this. So each step basically changes the current by a factor of 10, for example. So from here to say here, 1, 2, 3, 4, 5. So it's like 10 raised to 5 changes there. Okay, so 5 decades of change. Now, in digital devices, what we usually do is we apply 0 voltage in order to turn the device off, and we apply high voltage to turn the device on. Okay, so VGS equal to 0 is like low state, and VGS equal to say VDD is like high state. Okay, these are for digital application, and not, because our course is majorly on digital VLSI. So in digital VLSI, for an N channel MOSFET, we assume that VGS is equal to 0 means the switch is open, no current flows through it, and when VGS is equal to VDD, we have a high state at the gate input. Okay, so this is gate input. I am saying we apply low state means VGS is equal to 0, high state means VGS is equal to VDD, which is greater than VTH, and therefore the switch is closed. Okay, so here closed switch, the device will have an inversion channel and it will be acting like a closed switch. Here we have an open switch equivalent. Okay, so but if you really see the current, it's not going to be 0. As I said, the way I have shown here, 1, 2, 3, 4, 5. So 5 orders of magnitude means, suppose if the current is like say 10, so this is ID I am putting here, not log ID, because if you take the logarithm, logarithm of 10 micro, so you will get what? So this is 10 raised to minus 5, you will get something like minus 5. Okay, whereas here at this point, if I take logarithm, this will be like logarithm of 5 orders of magnitude means this is 10 raised to minus 5, so it is going to be 10 raised to minus 10. Okay, so that will give you minus 10. Okay, so from minus 10 to minus 5, okay, minus 10 then minus 9, minus 8, minus 7, minus 6, minus 5. So it goes like that, logarithmic scale goes like that, but the current is actually changing from, you know, say 10 raised to minus 4 micro to 10 micro. So the current at on condition is something like 10 micro. Okay, I mean it could be a different current also, maybe 1 milli also, but in the what is more interesting for us right now in sub-threshold operation, that is when VTH is equal to 0, we don't have a zero current, we have a finite current which is just 5 orders of magnitude you know, smaller than the actual current. So that current is what we called as sub-threshold leakage current. Okay, so point number 4 is basically sub-threshold leakage. So it is the so what is sub-threshold leakage current? So sub-threshold leakage current is the magnitude of drain current when VGS equal to 0, and ideally this should be as small as possible, but practically this is never 0. Okay, so how small it can be, that is what we are interested in looking at. So in order to find that out, we need to go into the details of sub-threshold operation. Okay, so let me again draw the schematic. So you have n plus here, another n plus here, and so we are looking at a case where we give the gate voltage small. Okay, so VGS less than VTH. This is the situation we are considering, and to be you know, if you look at the number of carriers inside, they are not much, right? It's not going to be much. It's going to be very, very small. Only when you reach VTH, it's going to be significant. But less than VTH, the concentration of these electrons. Okay, so inversion layer has not been created. So there is a weak inversion, probably you can say. So that will have some. So this is basically the point x equal to 0, and this is basically x is equal to L. So if you look at the concentration of electrons from so we need to apply a VDS also here, then only the current can flow. So we are going to look at the case where VDS is there, and the device is supposed to be off, but when VGS is less than VTH, but it is not really off. That's what we are saying. There is some current which is still flowing even when strong inversion is not happening. Okay, so when we operate in the sub-threshold region. So in order to see that, we need to look at the variation of the concentration from 0 to L. Okay, this is my x. So if you look at if VDS is very large, there will be pinch off happening also. So you will have variation of the concentration like this. That is, this side we have large concentration, and then to that side it will go to 0, because wherever the depletion region begins, you will have 0 concentration. That is why we call it as depletion region, because so there is a depletion region here also, so which I am not highlighting much because we are looking at another parameter here. So wherever the depletion region start, you will have zero concentration, but there will be a concentration on the source side relatively larger, and this concentration I will call it as the concentration of electrons in the p region as NP of 0. Okay, so 0 corresponding to x equal to 0, and then it reduces to 0. So here I can say that it is NP of L, which is 0. So you can see that there is a change in the concentration from left to right. And why there is going to be more concentration here? That's because we are applying a VGS, which is basically raising the potential of the surface. So surface will have a potential which is psi s. Okay, it may not be above VTH, but still when we derived the expression for threshold voltage, one thing that we assumed is that we are in the depletion mode of operation. So in depletion mode of operation, as you increase your VGS, then your psi s will go up, and as the psi s goes up, there is going to be more and more electrons coming in. Earlier the electrons were still there, something like 10 raised to 4, then it became like 10 raised to 10, 10 raised to 14, so it will keep on increasing, and when psi s become 2 phi b, that is when the concentration of electrons become equal to that of the bulk hole concentration. But before reaching there, still the concentration of electron is rising, and that is what is NP denotes, NP of 0 or NP of x. But since there is going to be a variation in the potential from left to right due to the application of VDS, this concentration will be reducing to the other side. Okay, it will be more on the left side compared to that variation we did not talk about earlier. But so that will come into play in the depletion region. These concentrations are going to be much lesser than the Na, that is the acceptor impurity concentration. So that is why we neglected it in the derivation for threshold voltage. But nevertheless, they are not 0. We have done some problems also where we showed that it is something like 10 raised to 14, which can be neglected in comparison with the 10 raised to say 16. Okay, so the charge is essentially due to the depletion immobile charges, but nevertheless they are non-zero, they are there. There is, so due to that there could be some current. Now since the current phenomena in a semiconductor is of two types, so whenever we talk about current, it could be due to either drift or it could be due to diffusion. Okay, so electron current can be due to drift of electron as well as diffusion of electron. Now if the concentration of electron is much smaller, okay, than Na, then IN drift is much lesser than IN diffusion. Okay, but when we derived the expression for drain current, but if N is greater than Na, it is the other way. IN drift is much larger than IN diffusion. Okay, so diffusion current depends upon this concentration gradient. Okay, whereas drift current depends upon the N value. So when N is in the subthreshold, so therefore in subthreshold, since NP is much less, we can safely neglect the drift current or the drift current component. Okay, earlier in our derivation we did not even take into account of the diffusion current because N is much larger and therefore the prominent contribution of the drain current is due to, it is going to be due to the drift current. Okay, N was much larger than your in the inversion layer, the concentration of electron is much larger than Na, and therefore the current is essentially due to the electric field. There is a potential variation, etc. But now what is going to happen is that the N value is much lesser compared to Na, and therefore the drift current contribution can be neglected. So the current, if at all it is flowing in the subthreshold operation, it is entirely due to the diffusion. And what is diffusion current? Diffusion current is basically due to the concentration carrier. So if I want to write the diffusion current, so this is the diffusion current. So it is given as Q into diffusion coefficient. Then you have what is called as concentration gradient. Okay, and so this will give you current density, and then multiply it with the effective area. So that is how you find out the diffusion current. So if you know NP of 0, then I can find out the slope. Okay, so if you approximate it as a linear line, which is a good approximation, especially when you have a smaller channel length, L is very small, and then any variation from NP0 to 0 can be approximated as a straight line. So what is this? So here dNP by dx is going to be change in the concentration, that is NP of 0 divided by what? Divided by L, right? Actually it is going to be negative, okay, but I'm just taking the magnitude of the concentration in order to not mess with the signs that would come up. Anyhow, we know that the direction of current is from right to left, because drain voltage, positive terminal is connected to drain, VDS positive voltage is connected to drain, and negative voltage is connected to the source. Okay, so this is the source and this is the drain, and the current is going to be in this direction, that we know. So let's just work out the magnitude of this current. So electrons are going to flow from left to right. Okay, this is the direction of electron flow, but current is in the opposite direction because electrons are negative charge carriers. So we will substitute this back into this equation. Okay, so the diffusion current, the diffusion current in subthreshold operation, that's what we are looking at, because neglecting the drift current, because drift current is going to be much smaller, because this absolute value of this carrier density is much smaller. So that is going to be equal to, so I can denote it as subthreshold. Okay, ID sub. Okay, so what is it? Q into dN into, now I will substitute NP0 divided by L into effective area. Now what is effective area? Effective area means the, when you look at the channel, the cross section of the channel, you know, the layer of electrons, it has some depth which is basically W, and then some thickness of this electron distribution. Okay, so that we don't know exactly how much is that area, so it may be a better idea to talk about this current density, but still if you want to find out the current, you need to multiply that current density with the current area of cross section. Okay, so this is basically current density, which means current per unit area. So multiply it with area of the cross section, that will give you the current. Okay, so this I can further write as Q into dN by L into area, effective area, and then what is NP of 0? So NP of 0 is, if you remember from our earlier discussion, it is NP0 into e raised to psi s by Vt. Okay, this is a expression that we have earlier looked at. That means it's called the law of junctions. Basically, when you rise the potential from the intrinsic concentration, which was basically Ni square by Na. Okay, so this can also be written as Qn area effective Ni square by L into Na into e raised to psi s by Vt. Okay, so the entire these are constants. I will call it as I0. I will take it as I0 into e raised to psi s by Vt. So I hope you remember this formula. So when the potential change, that is far down in the bulk, you have a potential which is 0, because we assume that the body is connected to the ground. But at the surface of the semiconductor oxide interface, we have a potential psi s. So by the change of voltage, how much is going to be the change in the electron? We have done this using the this formula, the problems also. How much when you apply say 100 millivolt psi s, how much is going to be the change in the concentration of electrons, etc. So if you want, you go back to the previous class and refresh it. So that NP0 basically depends upon Ni square by Na, which is the acceptor impurity concentration. Okay, all right. So this is what we will get. So all the constants here, Q, the Dn, L, Na, Ni square, all of these are constants. So I am putting it in as I0. So I0 into e raised to psi s by Vt. Now I want to connect the psi s to VGS, because we are ultimately plotting what? We are ultimately plotting the ID subthreshold. So that is ID subthreshold as a function of VGS. So how do I write it? I can write psi s as VGS by some n Vt. Okay, so where I have defined psi s as VGS by n. In other words, where n is basically a quantity which is greater than or equal to 1. So let me specify that n is basically greater than or equal to 1. So you are applying a VGS on the gate, then the channel potential or the surface potential, it should be called, is increased by some amount, but it can never be exactly equal to VGS. It will be lesser than VGS, okay, because there will be drop across the oxide layer also. So remaining is going to be the potential on the surface. Okay, so n basically is a tells you how much fraction of the VGS is going to be coming in the surface. Okay, so depending upon the way the oxide capacitor is made, you can make the surface potential maybe same as that of or lesser than that of your VGS applied. Okay, so if there is a good control of the surface potential with the VGS, then you can say the most ideal case is n equal to 1. So whatever voltage you give at the gate, that will immediately come at the surface of the semiconductor. Okay, so so that's basically n. So we have got this final expression. So this is what we are plotting. Now very important parameter here is called as subthreshold. Subthreshold slope. It is also called subthreshold swing, denoted by S. It is defined as dVGS by d log of ID. Okay, dVGS by log of ID. So ID subthreshold. Okay. So in order to so this will be a parameter which will determine the slope of our characteristics, subthreshold characteristics, which I have. Okay, where is it? I think here. Okay. Sorry. Where is it? The yeah, this one. Okay, this figure which I drawn with the logarithmic scale. Okay, the slope of this, we are going to estimate the slope. So how faster it will, reduce the current when you go from on state to off state is determined by the slope of this curve. So we are defining the slope like this: rate of change of VGS with respect to the change in ID. It's basically the inverse of the slope, you can say, inverse of the slope. So if it is inverse of the slope, we want this quantity to be as small as possible so that the slope will be maximum. Okay, sudden change is what is required, so that when you change the voltage, immediately the current will go so much near to zero. Okay, not slowly going to zero, but faster way going to zero. So in order to evaluate this, first of all we need to take the logarithm of ID sub. So if you take the logarithm, what will happen? You will have log I naught, which is a constant, plus we have VGS by NVT, and this is basically a logarithm with respect to base 10. Okay, so we will have a factor like this, log 10 to the base e. Either you multiply it with the log e to the base 10, or you divide it by log 10 to the base e. Okay, so this is what it is. And now we need to take derivative. So I will take a derivative of this. So ID sub to dVGS. So then what will happen? The constant will go away. So I will have 1 by NVT log 10 to the base e. Or in other words, according to my definition, I had S is basically inverse of this. S is basically, therefore, subthreshold slope. Okay, so that is going to be NVT log to the base, logarithm of 10 to the base e, and that is going to be basically 2.303. Okay, and VT you know already, that is 26 millivolt. So what is going to happen is that this is going to be N into 60 millivolt. That's what you will get. Okay, and what's going to be the unit? So unit, if you look at it, is dVGS by logarithm of ID. So this is per decade, because of the logarithm of with respect to 10. That means, what does that mean? For a change of 1 decade of current, it requires 60 millivolt. Okay, 60 millivolt multiplied by N. So if N is equal to say 1.5, that means your S is basically 90 millivolt per decade. Millivolt per decade. So that means if your so it means what? The implication is this: if for example, if your VTH is equal to 0.6 volt, or let's take yeah, let's take 0.6 volts. Then at VGS is equal to 0, what is going to be my ID sub? So it is going to be determined by how many 90 volts, okay, and I am taking again n is equal to 1.5. so how many 90 volts I need to decrease? So that will be so 600 divided by 90, okay, so 600 divided by 90, so that is 60 by 90, that is how much it is around, so 63 divided by 9 is around, so it's around 7. So that means 7 orders of magnitude I am going to reduce the current. So that means if it was ID for VGS above VTH, suppose if this is equal to say 10 milliampere, then when I make VGS equal to 0, or let us say this is VGS is equal to VTH, it is 10 milliampere, and when VGS is made to 0, it will become, it is changed by 7 decades. That means 10 raised to minus 7 multiplying 10 milliampere, okay, this many amperes. So that is how much? 10 raised to minus 9 ampere or nanoampere. So this is going to be 1 nanoampere. So that is how the current is going to change when I make. See, it is never 0. There is a leakage current. It is equal to 1 nanoampere for this particular problem which I have considered here. So this is a problem, an example problem that I considered. So we have found out this subthreshold swing or subthreshold slope, which tells you how many decades it will change in 90 millivolt. We had around 600 millivolt because our threshold is 0.6 means 600 millivolt. So for each 90 millivolt change, the current will change by a factor of 10. It will become 10% of its original value. So in 600 millivolt there are around 790 millivolts. So for each, if there is a reduction by a factor of 10, so we will reduce by a factor of 10 raised to 7 for the final current. When you switch off the device, by giving a 0 voltage at the gate, you will have 10 raised to minus 7 multiplied by whatever current which was there when you on the device. So it will be 1 nanoampere. So one thing you can see is that if the threshold voltage is larger, the off current or the subthreshold current when you make VGS equal to 0 is going to be very small. But on the other hand, if you redo this problem with say VTH is equal to 0.27 volt, if threshold voltage is 0.27 volt, so 270 divided by 90 is going to be just 3 orders of magnitude it will reduce. That means if it was 10 milliampere, it will become 10 microampere, okay, which is very significant. So for small threshold voltage, the off current is going to be much significant, but for large threshold voltage, the off current is really negligible because there is a lot of decades of reduction that is possible there. But on the other hand, when you make the device small, your power supply voltage is something like 0.8 volt these days. So you cannot have a large threshold voltage. Threshold voltage will be kept something like say 0.2 or 0.3. So you cannot have that at high voltage. Otherwise, there is no space for accommodating voltage change. Okay, in the aspect of noise in the circuit. So we need to have some gap available. So therefore we cannot really keep the threshold voltage very high when you scale the device to very smaller dimension. So that is a challenge. So there's a trade-off as you increase the threshold voltage, we can have a large change, or we can make the off current really small, but then the scaling will prohibit us from keeping the threshold voltage very large. So there is somewhere there is a trade-off that we need to keep